cause vacuum birefringence of light. And this was observed, this birefringence of light from a magnetard as it passed through the vacuum space due to the ordering dynamic that the strong magnetic field of the neutron star had on the vacuum structure. So this is another example of where the substantive nature of the vacuum has been directly observed. And an important thing to note is that particles that are produced in this way, like a particle-antiparticle electron-positron pair, are necessarily quantum entangled with each other. And so this is going to be important when we look at the intrinsic entanglement of the quantum vacuum and how that was leveraged for quantum energy teleportation. And when we consider the ER equals EPR holographic correspondence conjecture, that is Einstein-Rosen-bridges equals Einstein-Podolsky-Rosen correlations, wormholes equal entanglement, we're also talking about micro wormholes and quantum entanglement. And we're talking about these particles being generated from the vacuum structure. And there was a report on the holographic Schwinger effect and the geometry of entanglement, where they were showing how this mechanism of the Schwinger effect is a way to realize what's called the Wheeler wormhole. John Archibald Wheeler in quantum geometrodynamics, a unified physics, a quantum gravitational approximation of unified physics, he described electrons and positrons as a wormhole, as a particle pair, with the positron and electron as mouths of a connected Einstein-Rosen bridge through space. And that idea has, in this study, has been validated. So in the experiment, it was thought that the field strength necessary to produce these vacuum polarization effects would only be able to occur around neutron stars and black holes. So that kind of makes any earthbound laboratory experimental test of predictions like the Schwinger effect seemingly impossible. However, in a recent experiment, this was reported in the journal Science, an international team of researchers utilized a phenomenal property of graphene to observe the Schwinger effect for the first time and validate the Schwinger effect. Now, graphene has become a focus of material scientist research as it has remarkable structural and electronic properties. For example, it can carry huge current densities, about 10 to the 8 amps per square centimeter, roughly 2 orders of magnitude greater than copper. And even though it occurs in these single planar honeycomb configurations or sheets, it's remarkably strong. If rolled into a carbon nanotube, it's stronger than steel. Researchers have purported to observe superconducting properties in graphene, something that is usually only observed in supercooled metals or metal alloys. And this is opening the potential for room temperature superconductors. Another technological application that will have significant benefits for human civilization, room temperature superconductor. So in the experiment, these researchers constructed what are called graphene superlattices. Now in graphene, a vacuum exists at the point where the material's conduction and valence electron bands meet and no intrinsic charge carriers are present. So you have a kind of artificial vacuum set up. And in recent experimentation, this research team identified a signature of the Schwinger effect at this so-called direct point, observing pairs of electrons and holes, the solid state equivalent of positrons, created out of that vacuum space in the graphene superlattices. The team achieved this by constructing devices that are referred to as graphene superlattices, where essentially each planar crystalline lattice of carbon atoms are stacked but slightly misaligned, enabling nonlinear electronic interactions between atoms in the lattice. In these graphene superlattices, graphene's unit cell, the simplest repetition of carbon atoms in its crystal structure, significantly expands such that the crystal is stretched by a factor of up to 100 in all directions. This stretching dramatically changes the material's properties, enabling the researchers to produce electric field strengths of a quintillion volts per cubic meter or square meter. The team achieved this by constructing devices from what are known as the graphene superlattices and leveraging that kind of nonlinear interaction at that direct point. So via this kind of construction, they were able to directly observe the production of an electron-positron plasma and key signatures that demonstrated the realization of the Schwinger effect. Current voltage characteristics that resemble those of superconductors, sharp peaks in differential resistance, sign reversal of the Hall effect, and a marked anomaly caused by the Schwinger-like production of a hot electron hole or electron-positron plasma. So by applying strong electrical currents to the graphene superlattice-based devices with current densities up to 0.1 microampere per millimeter, the team was able to identify current voltage characteristics that only occur with the production of electrons and positrons. But one of the significant things of this experiment is that they didn't have to produce electric field strengths of 10 to the 18 volts per square meter. They were able to work with much more achievable current densities and leverage that kind of nonlinear behavior of these graphene superlattices, the conduction within these graphene superlattices, to generate a strong enough effect for vacuum polarization that a electron-positron plasma was generated from empty space, from the quantum vacuum. So where before there was just a vacuum in between the graphene superlattices, they generated an electron-positron plasma, a particle flux. Surprisingly, the team observed another unusual high-energy process that has, as yet, no analog in particle physics or astrophysics. When the researchers filled the vacuum and graphene with electrons and accelerated them to the maximum possible velocity allowed in the material, which is actually around 1/300th the speed of light. So it's not the speed of light in a pure vacuum. The electrons appear to become superluminous. So they exceeded that theoretical bound So 1/300th the speed of light is the maximum speed of light in